So this is the last topic of EEE123. We're going to take up transformers this week. How many of you know what a transformer is? Can I just see a show of hands? No? How many of you here know what a transformer is? Okay, so saan yun natutunan yung transformer, no? Can I hear from someone? Saan yung alam yung transformer?
Sir, physics po, nung high school.
High school. Okay. Sa mga bahay nyo, wala kayong mga transformer? Di ba madalas sa bahay, pag meron kayong appliance na galing sa US, 110, tapos yung voltahe nyo 220, then you need a transformer to transform from 220 to 110. We're going to focus on that type of transformer. Although there are really many types of transformers. You see transformers used in electronics, you see it used in power systems, you see it used for appliances, as part of electronic circuits and so forth. No? Okay, let's review first magnetic induction. So let's say I have a coil. So this is a coil consisting of n turns, no? And let's say I have a current I flowing in this direction in the coil. Okay, so nabanggit kanina physics. We know from physics that if you have a current that is flowing through a coil, then there's going to be a magnetic flux that is produced by that particular current. No? And the direction of the flux will follow the right-hand rule. No? What is the right-hand rule? If you get your right hand and you make your fingers coil or curl in the direction of the current, then the direction of your flux is what your thumb will point to. So if I do that for this particular coil, no, I make my fingers curl in the direction of the current. This is going to be the direction of my magnetic flux. It's going to be from inside the core of the coil. It's going to be from left to right, and then outside it's going to be from right to left. No? But most of the magnetic flux is going to concentrate in the middle of my coil. If my magnetic flux is changing with time, so if this flux is changing with time, then the magnetic flux is going to induce a voltage across my coil. So how does this magnetic flux change with time? That will change with time if your current is also changing with time. In other words, kung DC yung current natin, yung flux natin will not be changing with time, and therefore I will not induce a voltage. The voltage that is induced, E, is proportional to the rate of change of flux and proportional to the number of turns of the coil. In fact, the exact formula, excuse me for 10 seconds. Okay, again, no? The voltage induced is going to be proportional to two things. One is the number of turns of the coil, N, and the other is the rate of change of flux. In fact, this is the relationship between the voltage and N and dV by dt. No? This is also known as Faraday's law. And we know that N dV dt is also equal to L di by dt, where L is our inductance. So pinag-aralan na natin yung inductance. So that is magnetic induction. Okay, so I have here the same coil 1. I'm going to label it coil 1 because later on I'm going to introduce a second coil with N1 turns. What I do is, instead of having that coil just in the air or in the atmosphere, I wind my winding around what I call a core, no? A magnetic core. Okay. So what we use is usually what is called a low reluctance core. Ano yung reluctance? Reluctance is the tendency of a magnetic material to resist the flow of magnetic flux. You might liken it to resistance. Resistance is the tendency of a material to resist the flow of current. Reluctance is the tendency of a material to resist the flow of magnetic flux. Now we say a low reluctance coil. In other words, this material supports the flow of flux. So what happens now when I apply a source that creates a current flowing through coil 1? No? And the source I will apply is an AC source because I want my current to be changing with time. Because this is low reluctance, halos lahat ng magnetic flux dito lang pupunta. Konting-konti lang yung flux na magli-leak dito. No? There's going to be some flux here that's going to leak. There's also going to be flux here that will leak. But most of the flux will be confined to the core. So because this is an AC source, this flux is going to be varying with time. In other words, dphi dt is not equal to 0. Of course, the flux, the varying flux with time will induce a voltage across your coil. No? Will induce a voltage E1 across your coil. Now, what happens if I connect another coil to the same core? So this is a second coil connected to the same core, this time with N2 turns. This particular coil is going to experience the same flux, this same flux that was produced by I1. And because this flux is changing with time, expect that you will get a voltage induced also in your second coil. So note, no? I1 is the current that is supplied by this source, and I1 causes a changing flux which induces a voltage across coil 1. Okay? That is the self-induced voltage. No? But because this flux also, we call it links coil 2, then it will also induce a voltage across coil 2. We call this the mutually induced voltage. No? So this is self-induced and this is mutually induced. When nothing is connected to coil 2, so let's say this is an open circuit, walang nakakabit dyan, then the current I1 that will flow will only be to magnetize this core. In other words, itong I1 na to, maliit na maliit yan. No? It will only be to magnetize this core. Okay? And if the core has a very low reluctance, no, this one will be almost equal to 0. So the smaller the reluctance of the core, the smaller the magnetizing current. IEX, no? IEX is the magnetizing current. From Faraday's law, we already derived this earlier. E1 is equal to N1. N is the number of turns of coil 1, dphi by dt. Since it is the same flux, then we can conclude that E2 will be equal to N2, the same phi, no? The same flux, dphi by dt. This is under ideal conditions. So if I get the ratio of E1 to E2, that is just N1 over N2. The ratio of this voltage to this voltage will just be equal to the ratio of the number of turns of coil 1 to the number of turns of coil 2. Sometimes we give this the symbol, sorry. No? Sorry. Yeah. Sometimes we denote this by the letter A, no? Where A is what we call our turns ratio. Is the turns ratio. The ratio of N1 to N2, yun yung A. Okay, so going back to this particular setup, what will happen now if I connect a load to coil 2? Dati-dati, open circuit to. No? Walang current na magfo-flow sa coil 2. But because I connected a load there, expect a current I2 to flow. Okay, ang mangyayari, I2 will create a magnetic flux that opposes the flux created by I1. In other words, if you apply the right-hand rule to this particular coil, okay, if I apply the right-hand rule, note that the current that is flowing in the coil in the right will be in this direction. Okay, will be in this direction. It starts, you can think of it starting from the bottom, going around in the clockwise direction, and exiting at the top. If it is in this direction, the flux that I2 will produce will be opposite the flux phi, which makes sense. Because if I2 produces a flux in the same direction as phi, then phi will build up, and there's positive feedback, and it will just continue to build up and build up and build up, and your voltages will go to infinity. But because the flux created by I2 opposes phi, okay, it will oppose phi, the action of I2 will be to try to decrease the value of phi. Okay, but the setup wants to retain a certain value of phi. So what will happen? Because the setup is trying to retain a certain value of phi, ang mangyayari, I1 will increase. So earlier, without the load, nung wala yung load, I1 was very small. It was just the current needed to magnetize the core. But when I connect the load, because there's I2, this I2 will oppose this flux, and therefore I1 has to increase to sustain the flux. Okay, I1, as it says here, will automatically increase to sustain the flow of flux. And I1 will no longer consist of just the magnetizing current. Earlier, pag walang load, ang I1 magnetizing current lang siya. Okay, this is something that you're going to take up when you take up magnetic circuits. This is actually called a magnetic circuit. In a magnetic circuit, your flux is likened to current, reluctance is likened to resistance. And then the product of current and the number of turns is called your magnetomotive force. In electric circuits, that is likened, or the parallel of that, or the analog, analog of that would be your electromotive force or voltage. So, but don't worry about that now. No, I just have to introduce the concept of magnetomotive force, which is N times I. And the magnetomotive force produced in coil 1 should be balanced by the magnetomotive force produced in coil 2. So I have N1, I1 should be equal to N2, I2. Okay. Thus, I1 over I2 is equal to N2 over N1. If we use the symbol A, this is equal to 1 over A. Okay, to summarize, this is actually a transformer. Okay, this is a transformer. A basic transformer has two windings sharing a common core. The windings have N1 turns and N2 turns respectively. And the turns ratio is N1 is to N2, which we said we also use the symbol A to represent. N1 is called your primary. This is where the source is connected. And N2 is called your secondary. And this is where the load is connected. So usually, pag sinabing primary, doon nakakabit yung source. Pag sinabing secondary, doon nakakabit yung load. And for an ideal transformer, the AC voltages and AC currents will be related as follows. E1 over E2 is equal to N1 over N2. So this is the relationship between the voltage at the primary and the voltage at the secondary. And then I1 over I2 is equal to N2 over N1. The relationship between the current in the primary and the current in the secondary. E1 and E2, well, the way I showed it here, E1 and E2 are, and well, E1, E2, I1, and I2 are general AC voltages, no? So they can be the RMS value, they can be the time domain function, or they can be the phasor value. No? Now, E1 and E2 will be in phase. Note that if the ratio of E1 to E2 is a real number, no, because this is a real number, then E1 over E2 must be a real number. And therefore, E1 and E2 will be in phase. Same thing with I1 and I2. I1 and I2 will be in phase. However, E1 and E2, E1 and I1 are not necessarily in phase. E2 and I2 are not necessarily in phase. If we go back to, let's go back to this. Okay. The phase difference between E2 and I2 will depend on the load. For example, if your load is a pure inductance, what is the phase difference between E2 and I2? Can I hear an answer? Shout out lang. What if this is a pure inductance? Ano yung phase difference between E2 and I2? Nakalimutan na ninyo? Try to remember.
Sir, 90.
Exactly, no? 90 degrees, right? So if the phase difference between E2 and I2 is 90 degrees, yun din yung magiging phase difference ng E1 at saka I1. Because E1 is in phase with E2 and I1 is in phase with I2. No? So kung ano man yung phase difference between E2 and I2, yun din yung phase difference between E1 and I1. Okay, so that's what it says here. No? The phase angle between E1 and I1 will depend on the load. So this I already mentioned. The above relationships apply to the time domain expressions. They apply to the amplitudes. So here, based on my variable, this implies time domain, but I can use the same formula to relate the amplitudes of E1 and E2. I can use the same formula to relate the effective values of E1 and E2. And finally, I can use the same formula to relate the phasor values of E1 and E2 and I1 and I2. So are there any questions so far? So that is the basic concept of a transformer. Any questions so far? Okay, thank you for responding, those that respond. No? Okay, so let's just see whether you understood what I've taught you so far. No? So here's just a review question. You purchased a 100-volt appliance from Japan. So sa Japan, ang voltahe is 100 volts. No? Lahat ng mabibili mo sa Japan, 100 volts rated. Unfortunately, sa bahay natin, yung kuryente, 230 volts. Yun yung sinusupply ng Meralco. So to convert from 230 volts to 100 volts, you decide to wind your own transformer. So punta ka sa hardware store, bibili ka ng core, bibili ka ng kawad, you buy a bare copper wire, and then you decide to wind now your primary and your secondary. So if you have 1,000 turns in the secondary, how many turns are required in the primary? Can I hear an answer? Iba naman yung sumagot, no? Not the one that earlier answered.
2,300.
Yes, that's right, 2,300. No? So I guess this should be a no-brainer. No? So E1, we're talking now here about RMS value. No? E1 over E2 is equal to N1 over N2. No? 100 volts is our load side, so that's the secondary. So you have E1, and our source side is 230 volts, that is our primary. So our primary is 230 over 100 is equal to, I know that N2 is 1000. So what is N1? So N1 is just 2300. So this is just applying straight formula. E1 over E2 is equal to N1 over N2. Okay. Next question. The current drawn by the appliance should not exceed 10 amperes, and you wish to put a fuse in series with the primary to protect both the transformer and the appliance. What should the rating of the fuse be? So ano yung scenario na to? No? So we have our transformer. This is our transformer. So you have your primary, and you have your secondary here. So here, I have my load. And then this is 100 volts. And ang sinasabi dito sa problem to is we should not allow the load current to exceed 10 amperes. No? So IL max is equal to 10 amperes. Siguro baka masunog yung load if we allow the load current to. So what do we do? No? Dito sa primary, so this is my source. Okay, and this is 230 volts. Maglalagay ako ng tinatawag nating fuse. So how does a fuse work? The fuse has a rated current. If the current exceeds the rated current, we say the fuse will blow. This will become an open circuit. Masusunog yung fuse. And therefore, protektado ngayon yung transformer ko at saka yung load ko. So what should be the rating of the fuse? Again, just shout out an answer. Anyone? Ano yung magiging rating ng fuse ko? Walang gustong maghula? I'm just trying to wake you guys up, no? So, pindot-pindot lang sa calculator ninyo. Any answer, please?
$4.35 amp.
Yeah, about 4.3 amps. No? 4.3 amps. So how do you do this? No? So this is your, let's call this I1. Okay. I1 over IL will be equal to N2 over N1. No? Will be equal to N2 over N1. No? I1 over I2 is equal to N2 over N1. But N2 over N1, what is this? This is 100 over 230, no? Because our turns ratio is 230 over 100. So the reciprocal of that is 100 over, okay? But IL is equal to 10. Therefore, I1 is equal to 100 over 230 times 10. And if you compute that, 1,000 divided by 230, yeah, it's 4.35, no? Tama yung, mas precise yung sagot nung kaklase nyo, no? It's about 4.35 amperes. Of course, when you buy a fuse, madalang na makakabili ka ng 4.3, no? pag pumunta ka sa hardware store, you'll probably end up getting, in this case, you get a fuse not higher but lower. No? So you'll get a 4 ampere fuse. Because if you get a 4.5 or a 5 ampere fuse, then you're going to exceed your 10 amperes here. No? So you want to be on the safe side, so you get a 4 ampere fuse. But that's just practical aspects of when you try to protect appliances. So any question with regard to this? Basics of transformers. Okay, transformer ratings. This is typically found on a nameplate mounted on the transformer. So pag bumili ka ng transformer, okay, tignan nyo yung paligid ng transformer, you're going to find a nameplate somewhere there, and that's going to give you the ratings. No? So typically, anong nakasulat doon? It's going to tell you how many volt amperes your transformer is capable uh, how do you say this? Your transformer is capable of delivering. No? How many volt amperes is your transformer capable of delivering? What are the rated voltages? Usually the high voltage side and the low voltage side. No? So this is another way of specifying um, the side of the transformer. No, one way is saying primary and secondary. The other way is saying high voltage side and low voltage side. No? Because if you take a look at the transformer, again, kung babalik tayo dun sa, sorry. If we go back to, yeah, if you go back to this, if you take a look at this, no, your transformer is actually symmetrical. In other words, there's nothing that will stop you from connecting the source here and connecting the load here. Right? So in some applications, this might be your primary, this might be your secondary. But in other applications, this might be your primary and this might be your secondary. So sometimes, para walang confusion, they just say the high voltage side and the low voltage side. The high voltage side is the side with more turns, the low voltage side is the side with less turns. Okay. So going back to transformer ratings, so the transformer will specify the rated voltage, the high voltage side and the low voltage side. And these are the voltages for which the transformer was designed. And then the transformer will also tell you the rated currents on the high voltage side and the low voltage side. So these are the maximum allowable currents in either of these windings. And this should be consistent with the volt ampere. In other words, if I multiply rated current with rated voltage, I should get my volt ampere rating. Now, sometimes it's not the volt ampere that is specified, but the kilowatt. So what's the difference between volt amperes and kilowatt? You should know, no? Kilowatts or watts, rather, watts, no? Not kilowatts. Watts is volt amperes times power factor. So that's the only difference. So dapat alam na niyo yan. And then sometimes the transformer will also specify losses. So there are two types of losses. There are losses in the winding and there are losses in the core. We're going to talk more about that when we take up practical transformers. So this is how a nameplate might look like. Ganyan yung parang itsura ng nameplate pag nakita nyo yung transformer. If I zoom into this, yeah. I don't know if you can see it well, but you can see the kVA, you can see the volts at no load, and you can see the amperes. That's the rated amperes, okay? And then it has some other information, okay? And then it also has a diagram specifying the terminals and the different windings for the connected to the terminals. But the most important thing here is this information, okay? KVL, volts, and amperes. Any questions with regard to transformer ratings? Okay, so again, let's see if you understood what I discussed with you. A single phase transformer has the following nameplate data. The volt ampere rating is 50 kVA. The high voltage side voltage is 7620 volts, and the low voltage side voltage is 230 volts. Okay, so nasa nameplate yan. Okay. So the question is, determine the high voltage side and the low voltage side currents if operating at rated kVA with 230 volts applied to the low voltage side. So can somebody attempt this problem? Determine the high voltage side and low voltage side ratings if operating at rated kVA. In other words, no, when you say operating at rated kVA, it is delivering 50 kVA, okay, with 230 volts applied to the low voltage side. Anyone with the answers? Please try. No? I'm encouraging you to try to solve the problem. See if you understand the concepts. Yung mga hindi pa nag-attempt sumagot, no? Kahit na mali yung sagot ninyo, no? I just want you to try. Anyone? Shall I call out some names? What about, okay, I have some attempts here. Okay, the answer of John Edric is correct, no? Sa high voltage side. The answer of Peter is correct, both at the high voltage side and the low voltage side. No? So how do you solve this? Well, it's really just an application of the definition of kVA. No, if my transformer is delivering 50 kVA and 230 volts is the voltage at the low voltage side, what is my low voltage side current? No, your low voltage side current is just 50,000. That's 50 kVA divided by 230 volts. So 50 volt amperes divided by 230 volts, and that's going to give me 217.4 amperes. Okay. If I apply 230 volts at the low voltage side, I'm going to get 7620 volts at the high voltage side. Right? So my high voltage side voltage will just be 50,000 over 7620. And that's going to give me 6.56 amperes. Okay. Another way of doing it is, another solution is, okay, I low voltage over I high voltage is equal to V high voltage over V low voltage. No, remember that the ratio of secondary to primary current is equal to the ratio of primary to secondary voltage. Okay, and you're going to get the same answer. Okay, what about this? No? So here I tweak the question a bit. No, so here I'm saying it's operating at half its rated kVA, half its rated kVA, and I'm not applying 7620 volts to the high voltage side, but I'm applying 7,500 volts to the high voltage side. So what would be my high voltage side and low voltage side current? Okay, can you try again? Yung mga kahit na yung sumagot na kanina, no? Can you try again? What would be my high voltage side and low voltage side current? Yung mga hindi pa nakakasagot, no, please try to solve. Okay, I got the correct answer from several people, no? So tama yung sagot ni Chanel, tama sagot ni John, and tama yung sorry, Rick, your answer is not exactly right, but the answer of Mark is correct. Okay. So most of you got it right. No? Si Peter, half right. Okay. So the answer is the high voltage side would be 3.33 amperes. The low voltage side would be 110.4 amperes. So again, how did you solve this? No? So it's operating at half kVA, half its rated kVA. So that means that the high voltage side current, high voltage, will be, what is one half of its rated kVA? That's 25,000 volt amperes divided by 7,500 volts. And this is going to give you 110.4 amperes. Okay. Now, what is going to be your low voltage side current? No? Your low voltage side current, I low voltage, is going to be, okay, 110.4, okay, multiplied by 230 over 7620. This is 1 over A. No? This is, in fact, yeah, if your low voltage side is the primary, the high voltage side is the secondary, then this is going to be the secondary over the primary, or 1 over A. Okay, so you're going to get here 3.33. Are there any questions? So remember, this is 1 over A, no? This is 1 over A. Or how do you say this? In effect, this is E2 over E1. No? E2 over E1. Samantalang ito yung parang I1 natin, ito yung parang I2 natin. Any questions? Okay, good, no? At least I get the feeling na from your answers na nakakasunod kayo, no? Okay, let's talk about an ideal transformer. So I already drew this earlier. No, you have a source connected here, and a current I1 will flow. That current I1 will have two components. One would be to magnetize the core, but that's a very small component. And the other one would be to support the flow of I2. No? Because I2 will create a counter flux, and I1 would have to increase to sustain the original flux. So this is your two-winding transformer. Now, when does this become ideal? That is ideal if both coil 1 and coil 2 first have zero resistance. Remember that a coil is just wire that you wind around. No? You have a core, and then you wind around the wire. That is your coil. So it's essentially a wire. And if it is a perfect wire or an ideal wire, the resistance of wire is equal to 0. But we know that there's no such thing as a perfect conductor. So your coil will always have a certain amount of resistance. But in an ideal transformer, if we say the transformer is ideal, then we just assume that coils 1 and 2 have zero resistance. Okay, number 2, we assume in an ideal transformer that all the flux that is produced at the primary is only flowing through your core. In other words, there is no leakage flux. So sinabi ko na kanina that typically you're going to have some leakage flux. In other words, if this is my core, if I have a coil like that, so if this is your current I, so your flux is going to be in this direction, no? Your flux. Pero meron ka ring flux dito. Meron ka ring flux dyan. No? And in fact, meron ka ring flux dito sa mga maliliit na to. No? May mga flux ka dyan sa maliliit na yan. That's what we call the leakage flux. But if it is an ideal transformer, we neglect this flux. We consider practically all the flux to be just flowing in the core. And then the other assumption is that there is no heat loss in the core. Okay. And that the permeability of the core is infinite. What is permeability? No? Permeability is to magnetic circuits as conductivity is to electric circuits. Now, earlier, I said reluctance. Reluctance is to magnetic circuits as resistance is to electric circuits. So you might think of permeability as something like the reciprocal of reluctance, just like conductance is the reciprocal of resistance. If your permeability is infinite or your reluctance is zero, then the exciting current is zero. Then you don't need any current supplied at the primary to magnetize the core. Kasi konting-konting current lang, katiting na current lang, magnetize na kaagad yung core natin. So that these are the characteristics of an ideal transformer. And most of the time, we are able to use the ideal approximation of the transformer for practical circuit calculations. Now, when we have to consider some of these things, then we're going to go to the practical transformer, which will be discussed later on. This is the circuit representation of your transformer. Sometimes we put this symbol in to signify that it is an iron core. In fact, different core material, nag-iiba itong nasa gitna. No? Pag ganito, this is a general transformer, or you might even think of it as an air core transformer, no? Air core. But typically, sa mga transformers for electrical appliances and electrical distribution, it will have an iron core. And then the other thing that's important in your transformer is what we call your dot markings. These are your dot markings. So ano yung dot markings? If these are my dot markings, if the polarity of my voltage at the primary is from positive to negative, positive at the dot, then the polarity of the voltage at my secondary will also be from positive to negative, where positive is at the dot. So the dot markings will specify the relative polarity of the primary and secondary voltage. And then the other thing that is specified is your number of turns, N1 and N2. Sometimes, instead of the number of turns, basta ang ini-specify is A. No? So you'll see A, or A is to 1, meaning to say A is the ratio of N1 to N2. So this is N1 over N2. Okay, the dot markings are dictated by the way the coils are wound around the core. No? In other words, if this is the way I wind my winding, so dito it is wound dito clockwise, no? Dito it is wound counterclockwise. So dun sa left it's clockwise, dun sa right it's counterclockwise. Ito yung magiging dot markings ko. On the other hand, if I wind it this way, if I wind this way and this way, ito yung nagiging dot markings ko. Okay? So importante yung dot markings, no? Because if you, for example, no, if you follow the dot markings, then you know that E1 and E2 will be in phase. In this case, kung mali yung dot marking natin, we assume, let's say, that this is the dot, but the coil is wound this way, ang E1 will be 180 degrees out of phase with E2. Or E1 will always be the negative of E2. So the dot markings are important. Analyzing circuits with transformers. So this is our two-winding transformer. This is a typical circuit, a source connected to the primary, a load connected to the secondary, where the load is a general impedance, meaning to say it can have a real part and an imaginary part. Okay. We draw now the circuit equivalent in phasor form, in phasor domain. So this is now using the circuit symbol for the transformer, okay, and then showing all the quantities in frequency domain. So phasor voltage, phasor voltages, phasor currents, and impedances. Okay, so how do you analyze such a circuit? So assuming the transformer is ideal, we already know that the phasor E1 over the phasor E2 is N1 over N2, and the phasor I1 over the phasor I2 is N2 over N1. Okay. If I want to express E1 and I1, just expressing E1 in terms of E2 and I1 in terms of I2, I have these two expressions. So this is a no-brainer. Now let Z equivalent be the equivalent impedance seen by the source. No? So ano yung Z equivalent? Ito yung source natin. Ang Z equivalent is yung nakikita ng source dito. No? Z equivalent. In other words, from the point of view of the source, imbis na nakakabit sa kanya ito, ang nakakabit sa kanya is an impedance equivalent to Z equivalent. What is Z equivalent? Z equivalent is your phasor voltage Vs divided by your phasor current I1. Right? That is the equivalent impedance that is seen by the source. So Vs over I1, which is actually E1 over I1, because Vs is equal to E1. But expressing now E1 and E2 in terms of E2 and I2, so I'm just substituting these relationships here. Okay, here. Okay, I'm going to get Z equivalent is N1 over N2 squared E2 over I2. N1 over N2 squared E2 over I2. Since E2 over I2 is VL over I2, so pag dinignan natin to, no? E2 is the same as VL. VL over I2 is actually just Z of L. E2 over I2 is just Z of L. Then Z equivalent is N1 over N2 quantity squared times Z of L. No? So what is this? From the point of view of V of S, this is what it sees. Ito yung nakikita ng V of S. Z equivalent, no? Where Z equivalent is just N1 over N2 squared Z of L. Or sometimes we say A squared Z of L. No? You remember yung use natin ng A? A is N1 over N2. And we say the load impedance has been referred from the secondary to the primary. So here's an example. The transformer has a turns ratio of 1000 to 100. 1000 to 100. So the high voltage side is 1000 turns. The low voltage side is 100 turns. The RMS value of the source voltage is 220 volts. So this is 220 volts RMS. Okay. If Z's of L is 4 plus J3, what is the RMS value of the source current? Okay. So what do we want to do here? Okay, we want to refer itong value ng Z's of L from the secondary to the primary. Okay. Let Z's of L prime be this referred impedance. So Z's of L prime is just N1 over N2 squared Z's of L, which is 400 plus J 300. No? Because ang turns ratio natin is 10. Our turns ratio is 10. Okay. So 10 squared is 100. So I just multiply 4 plus J3 by 100. I'm going to get 400 plus J 300. And now this is my equivalent circuit. Ang nakikita ng V's of S, ang nakikita nito is just an impedance equal to 400 plus J 300. Now, sorry. How do we solve now for the RMS value? So ang hinihingi is the RMS value of the source current. I don't have the solution here, no? But what we can do is this, no? We can let Vs be our reference phasor. Ano yung ibig sabihin ng reference phasor? I explained this already before, no? When no angle is given, and we're just computing for RMS value anyway, so dito RMS value lang naman ang hinahabol natin for the current, we can assign an angle to any particular voltage in the circuit and make that our reference phasor. And of course, the most convenient angle to assign is 0. No? So in this case, we'll have V's of S at an angle 0. No? V's of S is going to be 220 volts at an angle 0. And therefore, I's of S is just V's of S over ZL prime. So this is 220 at an angle 0 degrees over 400 plus J 300. Okay, and I have the answer here, no? If you enter this in your calculator, this is 0.44 at an angle minus 36.87 degrees amperes. So ito na yung sagot ko. This is already the RMS value of my current. 0.44 amperes is the RMS value of my source current. Any question? Any question? Okay, so again, no, just to continue. So we already developed these equations before. Okay, we developed these equations. We expressed E1 in terms of E2 and I1 in terms of I2. Now let's say I multiply this equation with the conjugate of this equation. In other words, I multiply E1 with the conjugate of the left side of this equation, so the conjugate of I1, and I multiply this to N1 over N2 E2 by the conjugate of the right side of the equation. I'm going to get this. Or, ito nagka-cancel out, N1 over N2 cancels out with N2 over N1. I get E1 I1 conjugate is equal to E2 I2 conjugate. Anong ibig sabihin nito? First of all, what is E times I conjugate? You recall? What is E times I conjugate?
Sir, power.
Yes, no? That's a complex power, no? To be more precise. Pag sinabing power kasi usually watts lang yan, ano? So that's complex power. So, ang ibig sabihin nito, P1 plus JQ1 is equal to P2 plus JQ2. Okay, this is a very important observation. The power and the reactive power delivered by the source is equal to the power and reactive power received by the load. The transformer, ang trabaho ng transformer is just to transfer whatever it receives from the source to the load. The transformer itself does not, if this is an ideal transformer, it does not absorb any real or reactive power. In other words, ang trabaho nito, kung ano man yung natatanggap niya, pinapasa lang niya. Tagapasa lang siya. Wala siyang inaako para sa kanya, no? Basta kung ano man yung pumasok, ilalabas niya. So the power it receives, it gives to the load. The reactive power it receives, it gives to the load. No? That is your ideal transformer. Okay, so here's another example. No? Find the power and reactive power supplied by the source. So I have this particular source. Okay. This is again typical of a scenario where you have long transmission lines. So this looks like a transmission line, no? And then somewhere in your distribution system you have a transformer, and then here you have another transmission line. So this represents another transmission line, and then you have your load. And then in this case, your load is 8 plus J6, and your source is 220 volts RMS. Okay, so what you want to do is you want to simplify the computation of this. So I'm going to refer all of these impedances. I'm going to refer all of these impedances to the primary. So how do I do that? No, let Z2 prime and ZL prime be Z2 and ZL referred to the primary. Okay, what is Z2 prime going to be? Z2 prime is going to be N1 over N2 squared multiplied by Z2. Okay, what is N1 over N2? My turns ratio is 2:1. Therefore, N1 over N2 squared is 4. So this is going to be equal to 4 times Z2 or 1.2 plus J 1.6 ohms. The same way, ZL prime is going to be N1 over N2 squared multiplied by ZL. So again, that's 4. 4 times 8 plus J6. So I'm just going to get 32 plus J 24 ohms. So this is now going to be my equivalent circuit. Ang nakikita ng VS, of course, you have Z1, kasi nakakabit talaga yan dito sa primary. This is Z1. No? And then you have Z2 prime, and then you have ZL prime. Okay, so IS is equal to VS over Z1 plus Z2 prime plus ZL prime. Now what we do is we let VS be our reference phasor. So we need to say VS is equal to 220 at an angle 0 degrees volts. Okay, so finally I'm going to get IS. This is just going to be 220 at an angle 0 degrees divided by Yung Z1 ko is 1.6 plus J 1.2. Z2 prime is 1.2 plus J 1.6. And ZL is going to be 32 plus J 24. And I'm going to get 5.01 at an angle of minus 37.6 amperes. Okay. Ano ba yung hinihingi? Kalimutan ko yung hinihingi. Ano? Find the power and reactive power supplied by the source. Find the power and reactive power. So, what is now my power and reactive power supplied by the source? Medyo review na rin to from ano, no? Module 12. How do I get power and reactive power now? Anyone? Can I hear from, iba naman, no? Can I hear from Chanel? How do I get power and reactive power? Chanel, are you around? What about Eric? Are you around? How do I get power and reactive power?
Um, by using equation for complex power.
Yan, pwede, no? So, complex power, okay, S of the source is equal to V of the source multiplied by I of the source conjugate, no? So this is just going to be 220 at an angle 0 degrees multiplied by, ano yung conjugate ng I of S? This is 5.01 at an angle. Kung ano man yung angle ng I of S, babalik tayo natin. So 37.60 degrees. Okay. And I'm going to get 873 plus J 672.3. This is volt amperes. So this is now PS and QS, no? PS plus J Q sub S. So that's one way, ano? The other way is, alam naman natin na P is VI cosine theta. No? What is theta? And Q is VI sine theta. No? Where theta is the angle of the voltage, which is 0, minus the angle of the current, which is minus 37.6 degrees. No? And V is simply 220 and I is simply 5.01. So you can use either this formula or you can use this formula. No? Anyway, you're going to get 873 watts and 672.3 bars. Ito, no? Like I said, no, madali na ngayon mag-complex power dahil kayang-kaya niyong pindutin sa calculator ninyo. No? Nung panahon kasi namin, wala kaming calculator. So we tended to use this formula more. But I guess nowadays, people tend to use this formula more because it's so easy to use your calculator to do it. Okay, by the way, no, this is just an alternative solution. I could have referred Z1 and the voltage source to the secondary side. Kasi ang ginawa ko, I referred, what I did was I referred the load and Z2 to the primary. The other thing that I could have done was from the primary, i-refer ko sa secondary. No? So this is going to be my equivalent circuit. No? So what is Z1 going to be now? No? Z1 prime is going to be, okay, since I'm referring from primary to from primary to secondary, it's now going to be N2 over N1 squared times Z1, right? And this is going to be 0.4 plus J 0.3 ohms. Okay, and then Vs prime, I'm just going to use my turns ratio. No? This is N2 over N1 times Vs. So this is going to be 110 at an angle 0 degrees. No? Kasi remember, our turns ratio is 2:1. No? So kung yung primary source voltage natin used to be 220, pag refer mo yan sa secondary, magiging 110. And I'm using 0 because it's my reference phasor. Okay, if I compute for uh, S of S prime, which is equal to Vs prime IL, okay, I'm going to get exactly the same thing, 873 plus J, 672.3 volt amperes. Why? Kasi kung ano man yung tinanggap ng source na power at reactive power, yun din yung matatanggap ng load. In other words, the transformer is transparent to power and reactive power. The transformer will just transmit it. So whatever we compute, if we had referred from secondary to primary, that's also what we would have computed if we refer from primary to secondary. Okay, here's another example. Maybe this is the last example that I can discuss. No, the load consumes 1 kilowatt. So ito yung load at 0.85 power factor lag. 1 kilowatt at 0.85 power factor lag. What are the real and reactive power delivered by the source? So we assume that the transformers are ideal. No? So we have two transformers here, T1 and T2. Okay. The turns ratio of the first transformer is N1 is to N2, and the turns ratio of the second transformer is N3 is to N4. My question is this. Do we have to know N1, N2, and N3 and N4 to determine the power and reactive power delivered by the source? Do we have to know that? Anyone? I have an answer from Rick. Bakit, Rick? Bakit no?
Kasi walang ina-absorb yung transformers na power.
That's right, ano? Kasi kung ano man yung, remember what I said, no? Kung anong tinatanggap ng T1, pinapasa lang niya, no? So yung tatanggapin ng T1 from the source, papasa niya sa T2. Yung tatanggapin ng T2 from T1, papasa lang niya dito. So kung ano man yung power at reactive power dito, yun din yung power and reactive power na binibigay dito, no? So the solution here essentially is we really just apply the power triangle, no? So the load is 1 kilowatts. That's 1 kilowatts. Okay. Your power factor is 0.85 lag. So this angle is the arc cosine of 0.85. So all we have to do is compute for Qs of L. So what is Qs of L? Your Qs of L is just piece of L tangent of your arc cosine of 0.85. And this is going to give me 619.7 bars. Okay, and we know that piece of L is equal to 1000 watts. Okay, so I hope nakikita nyo, no? Because Q over P is the tangent of this angle. No? So Q over P is the tangent of that angle, and that angle is the arc cosine of 0.85. So piece of S is just equal to piece of L, and Qs of S is equal to Qs of L. No? So the load voltage and the transformer turns ratio are immaterial to the solution. I have some other examples, pero wala nang, let's see, no? I have one more example. The load L consumes 1 kilowatt at 0.95 power factor lead. It is supplied through a transformer with 2080 turns at the source side and 110 turns at the load side. Okay. Um, yeah, maybe what I can do is I can just leave this up to you, no? Because we might not have enough time to. But actually, this is not that difficult problem, no? Um, are there any questions? Any questions so far? I have the answer here. No? Okay. Now, this is what I want to mention. Ano? This material is not, again, no? This is not the official material that was published in UVLE. If you take a look at, I don't know if you've taken a look at the material already in UVLE. If you take a look at the material in UVLE, it's quite long. I think I counted 98 slides. So I just picked up these slides from, I just pieced them together from previous courses that I've taught, some of them service courses. I pieced all of this together and I'm presenting this to you again as supplementary material. But the official material, take a look at what is in UVLE. That is much more comprehensive. Okay. So I'm going to do the same thing also next week. No, I'm just going to pick up some examples and use it to illustrate to you certain concepts. Okay, having said that, if you have no questions, I'm going to close the session as soon as the last person leaves to give anybody that wants to ask questions an opportunity to do so. So that's it for this afternoon.